Hello, and welcome to Space for Sleep. Asteroids are what remains when planet formation stops before the final act. The solar system contains 8 planets, and it also contains an enormous amount of material that never became a planet. This material, rocky, metallic, sometimes icy, ranging in size from microscopic dust grains to objects hundreds of kilometers across, populates several distinct regions of the solar system, drifting in stable orbits or being gradually nudged by gravitational perturbations into new trajectories that occasionally bring them close to Earth or into the inner solar system. We call the larger pieces asteroids, and they are far more interesting, far more diverse, and far more scientifically important than the word rubble in their informal description might suggest. Asteroids are not a uniform population. They range from ancient, pristine fragments of the solar system's original building material, carrying water and organic molecules that may have contributed to Earth's oceans and the chemical precursors to life, to the processed cores of proto-planetary bodies that were heated and differentiated, then shattered in collisions, exposing their metallic interiors. They include objects that are solid, compact rock, objects that are loosely bound rubble piles held together by their own weak gravity, objects with moons, objects in pairs and triplets, objects that spin so fast they are constantly shedding material from their equators, and objects wrapped in craters and boulders that tell stories of a violent early solar system. They were the raw material of the planets. The inner planets, Mercury, Venus, Earth, Mars, assembled from the collisions and accretions of objects like the asteroids that remain today. Most of the original asteroid belt population was either swept up by the planets, ejected from the solar system by gravitational perturbations from Jupiter, or still drifts in the main belt. What remains is a sampling of the early solar system's rocky material, preserved in various states of processing and alteration, available for study both from Earth-based telescopes and from the growing fleet of spacecraft that have visited them. They are also, occasionally, hazardous. The Chicxulub impactor that ended the age of non-avian dinosaurs 66 million years ago was almost certainly an asteroid. Smaller impacts have occurred throughout recorded human history and prehistory, and the possibility of a significant future impact is taken seriously enough that governments and space agencies have established monitoring programs and are developing deflection technologies. Understanding asteroids is therefore not only scientifically interesting but practically relevant in a way that differentiates them from most other objects in the solar system. The story of asteroids is therefore not a side note to the story of planets. It is the unfinished part of planet formation left where we can still reach it. To understand asteroids is to understand why the planets formed where they did, why Earth received water and organic material, why some early worlds melted and differentiated while others remained primitive, and why planetary defense is now a practical branch of astronomy rather than a science fiction idea. There is a useful way to hold asteroids in the mind. A planet is a completed sentence. An asteroid is a surviving draft. It has not failed because it never became large. Its smallness is what makes it scientifically valuable. Planets hide their beginnings beneath volcanism, atmospheres, oceans, plate tectonics, weathering, and billions of years of internal heat. Asteroids preserve beginnings more directly. Some are fragments of bodies that almost became planets. Some are pieces of shattered cores. Some are carbon-rich archives of water and prebiotic chemistry. Some are loose piles of broken rocks so fragile that a spacecraft can sink into them like dry snow. This is why asteroids are not merely the leftover rubble of planet formation. They are the record of planet formation written in rock, metal, ice, salts, organics, craters, rotation states, and orbits. Their importance comes from the fact that they are incomplete. They let us see stages of planetary history that no full-sized planet can show clearly anymore. To understand asteroids properly, it helps to go all the way back to the first solids in the solar system. Before there were planets, there was a disk. Around the young sun, gas and dust orbited in a flattened, rotating nebula. Most of the mass was hydrogen and helium, but the dust carried heavier elements: silicon, magnesium, iron, nickel, sulfur, carbon, oxygen, aluminium, calcium, and many others produced by earlier generations of stars. At high temperatures close to the young sun, the first refractory minerals condensed, calcium aluminium-rich inclusions, often called CAIS. These tiny mineral objects are among the oldest dated solids and meteorites, about 4.567 billion years old, and they mark the beginning of the solid record of the solar system. After the CAIS came chondrules, millimeter-sized droplets of once molten silicate rock, flash-heated and cooled in the solar nebula by processes that are still debated. Chondrules are found in chondritic meteorites, the primitive meteorites that have never been melted into differentiated rock. Their presence tells us that the early solar nebula was not a quiet, cold cloud of dust gently settling into planets. It was a dynamic environment with shocks, heating events, collisions, turbulence, and rapid cooling. The smallest pieces of the solar system were processed by intense events before they ever became part of larger bodies. Dust grains stuck together. Pebbles formed. Pebbles concentrated into dense clumps, possibly through streaming instabilities in the gas disk, a process where solids and gas interact aerodynamically in ways that cause particles to gather into filaments. Once a concentration of pebbles became dense enough, gravity could take over and collapse the clump directly into a planetesimal kilometers or tens of kilometers across. This was an important change from older ideas in which dust simply stuck grain by grain all the way up to asteroid size. Modern planet formation models suggest that gravity-assisted pebble concentration may have been essential for jumping the difficult size gap between small dust and self-gravitating bodies. Those planetesimals then collided, accreted, shattered, heated, and sometimes differentiated. Some grew into planetary embryos. Some were consumed by larger bodies. Some were scattered away. Some survived, altered but not destroyed, as asteroids. In this sense, an asteroid is not only a fragment of a failed planet. It may be a fragment of a planetesimal population that existed before planets as we know them were assembled. The discovery history of the asteroid belt also changed the meaning of the word planet. When Ceres was found in 1801, it was initially treated by many as a new planet. Then Pallas was discovered in 1802, Juno in 1804, and Vesta in 1807. The region between Mars and Jupiter was no longer a clean gap filled by one missing planet. It was a zone containing several small bodies. As more were discovered in the 19th century, astronomers gradually stopped treating them as planets and began calling them asteroids, star-like objects, because through telescopes they appeared as points rather than disks. The name is slightly misleading physically, but historically understandable. They looked like stars that moved. That shift is important because classification in astronomy often changes when the population changes. One object can be an exception. 100 objects become a category. Thousands become a population with statistics, families, gradients, and dynamical structure. Asteroids became scientifically powerful not only because individual objects were interesting, but because the population was large enough to reveal patterns. Ceres' later reclassification as a dwarf planet after the 2006 International Astronomical Union definition change is another reminder that categories are tools, not truths carved into nature. Ceres is both the largest asteroid belt object and a dwarf planet. Vesta is not a dwarf planet, but is geologically more planet-like in some respects than Ceres. Psyche may be more core-like than either. Nature presents objects first. Human categories follow imperfectly afterward. The asteroid belt occupies the region between Mars and Jupiter, from roughly 2 to 3.5 astronomical units from the Sun. It contains roughly 1 to 2 million asteroids larger than 1 kilometer in diameter, and many more smaller objects down to pebble and dust scale. Despite their large number, the asteroids are spread across an enormous volume of space, and the belt is far less densely populated than popular imagery, influenced by science fiction depictions of spacecraft navigating cluttered debris fields, suggests. The total mass of the asteroid belt is only a few % of the mass of the Moon. Ceres alone contains roughly a quarter to a third of the belt's mass, and the 4 largest bodies, Ceres, Vesta, Pallas, and Hygeia, contain a large fraction of everything there. The asteroids are spread so thinly across their vast orbital region that spacecraft transiting through the belt face essentially no greater collision hazard than they do in the general inner solar system, a fact confirmed empirically by every spacecraft that has crossed the belt since Pioneer 10 in 1973. The belt exists where it does because Jupiter's gravitational influence prevented the material there from ever assembling into a planet. In the simplest account, Jupiter's gravity stirred up the velocities of planetesimals in the belt to the point where their mutual collisions were destructive rather than constructive. Instead of sticking together and growing, they shattered each other, and the debris was gradually swept away. The cascade of collisions over billions of years progressively ground the belt material down, reducing the total mass and fragmenting the larger bodies. The belt we observe today is enormously depleted relative to what was probably present in the early solar system. Estimates suggest the original asteroid belt contained roughly 1,000 times more mass than it does today, most of which was either accreted by the planets, scattered into other orbits, or simply ground into dust too fine to represent significant mass. Jupiter's gravitational influence creates a distinctive structure within the belt, specific orbital distances where the orbital period is a simple fraction of Jupiter's orbital period produce what are called mean motion resonances, and these resonances correspond to regions where Jupiter's gravitational perturbations are systematically applied at the same point in each orbit, gradually building up large enough perturbations to destabilize any asteroid in that location. These resonances produce the Kirkwood gaps, regions conspicuously depleted of asteroids visible in plots of asteroid orbital semi-major axis against number. The Kirkwood gaps divide the asteroid belt into several recognizable regions: the inner belt, the middle belt, the outer belt, and transitional zones at the gaps. The asteroid population in each region has distinctive characteristics, partly reflecting the initial conditions for formation at different distances from the Sun, and partly reflecting the different dynamical histories experienced at different locations within the belt. Resonances are one of the reasons the asteroid belt is not a smooth ring. The simplest resonance is a mean motion resonance, where an asteroid's orbital period has a simple ratio with Jupiter's. In a 3-to-1 resonance, for example, the asteroid completes 3 orbits for every 1 orbit of Jupiter. That means Jupiter's gravitational tugs arrive in a repeated rhythm, not randomly distributed around the orbit. Over time, those rhythmic tugs can increase the asteroid's orbital eccentricity until it crosses the orbit of Mars or Earth or is ejected into a different dynamical path. There are also secular resonances, involving the slow precession of orbits rather than simple period ratios. These can also pump eccentricities and inclinations, moving asteroids out of stable belt locations and into planet-crossing orbits. The famous Nu 6 secular resonance near the inner edge of the belt is one of the key escape hatches through which main belt material can enter the near-Earth population. This makes the asteroid belt a dynamic reservoir. It is not simply a storage shelf. Collisions create fragments. Yarkovsky drift moves fragments. Resonances remove fragments. Some become meteorites. Some become near-Earth asteroids. Some fall into the sun. Some strike planets. The belt is constantly leaking material into the inner solar system, though slowly by human standards. The distribution of asteroid types across the belt follows a systematic gradient. In the inner belt, closer to the sun, silicate-rich S-type asteroids, rocky, relatively bright objects composed primarily of olivine, pyroxene, and metallic iron, dominate. Moving outward through the belt, the C-type asteroids, dark, carbon-rich, water-bearing objects more closely related in composition to the Sun's overall non-volatile elemental abundances, become increasingly common, dominating the outer belt. The gradient reflects the thermal conditions in the original solar nebula. Closer to the Sun, where temperatures were higher, volatile materials were evaporated, and the solids that condensed were rocky and dry. Farther from the Sun, lower temperatures allowed water and carbon-bearing compounds to be incorporated into the accreting planetesimals. The asteroid belt samples this thermal gradient, preserving a record of conditions across a range of distances in the early solar nebula. The asteroid belt also teaches one of the first important lessons about the solar system. Location is destiny, but not destiny alone. The material that formed closer to the Sun was heated more strongly and lost more of its volatile inventory. The material farther out retained more water, carbon compounds, and chemically primitive material. But the belt was not a perfect set of separate shelves. Early migration of the giant planets, turbulent gas flows in the solar nebula, and billions of years of collisions mixed material from different formation zones. That is why the belt contains dry, rocky S-types, carbon-rich C-types, metal-rich objects, basaltic fragments of differentiated worlds, and icy or hydrated bodies that look more like outer solar system material than like inner solar system rock. The belt is therefore both a map and a shuffled archive. It remembers the temperature gradient of the young solar nebula, but it also remembers the violence that disturbed that gradient. The classification of asteroids is based primarily on their spectroscopic properties, the way they reflect sunlight at different wavelengths, which reveals information about their surface composition. The standard taxonomic system identifies several dozen distinct classes, but a few dominant categories account for most of the asteroid population. S-type asteroids, silicaceous, are the second most numerous and include most of the bright, well-known asteroids of the inner belt. They have reddish spectra due to the presence of iron-bearing silicate minerals and have modest albedos around 15 to 25%. S-types are compositionally similar to the ordinary chondrite meteorites, the most common type of meteorite found on Earth, making them the most numerous type of material falling on our planet. Objects like Gaspra, Ida, Eros, and Itokawa, several of which have been directly visited by spacecraft, are S-type asteroids. C-type asteroids, carbonaceous, are the most numerous overall, comprising roughly 75% of the known asteroid population. They are dark, with albedos typically of 3 to 9%, and have nearly flat, featureless spectra suggesting carbon-rich, hydrated mineral surfaces. C-types are compositionally related to the carbonaceous chondrite meteorites, which are among the most chemically primitive and scientifically valuable meteorites known, containing water, organics, and pre-solar grains. The most famous missions to carbonaceous asteroids, Hayabusa 2 to Ryugu and OSIRIS-REx to Bennu, both targeted C-type objects, and the samples returned from both have been among the most scientifically illuminating asteroid materials ever examined. M-type asteroids, often called metallic, are less common but scientifically fascinating. Older interpretations treated many of them as possible exposed metallic cores of differentiated parent bodies that were catastrophically disrupted in collisions, stripping away rocky mantle and crust. Modern observations are more cautious. Some M-type asteroids are genuinely metal-rich, while others appear to be mixtures of metal, silicate material, and impact-delivered carbonaceous material. Psyche, the large metal-rich asteroid in the middle belt, is the most important test case. NASA's Psyche mission, launched in October 2023, is currently en route and is expected to be captured by Psyche's gravity in late July 2029 before beginning its prime science mission in August. It will help determine whether Psyche is an exposed core, a metal-rich remnant, or something more complex than either simple label suggests. V-type asteroids, Vestaloids, are associated with the large asteroid Vesta and share its distinctive basaltic surface composition, produced by volcanic activity in Vesta's early history. Vesta is an unusual object in the asteroid belt, large enough to have undergone melting and differentiation in its first few million years, developing a metallic core, a rocky mantle, and a basaltic crust, processes normally associated with full-sized planets rather than modest-sized asteroids. The HED meteorites, howardite, eucrite, diogenite, are fragments of Vesta's surface, excavated by impacts and eventually finding their way to Earth, and they have been studied by meteorite scientists for decades as examples of basaltic igneous rock processed through the volcanic history of a small solar system body. Beyond these main types, the P-type and D-type asteroids of the outer belt and the Trojan and Hilda populations have featureless, very red spectra indicative of the most primitive organic rich material in the solar system, objects that have experienced minimal thermal processing and preserve the most direct record of outer solar system composition. DART also changed the public meaning of asteroid science. Before 2022, asteroid deflection was a plausible idea supported by physics and modeling. After 2022, it was a demonstrated technique. Humanity had changed the motion of a natural body in space on purpose, measured the result, and learned that the asteroid's own ejecta could do much of the work. That does not make planetary defense easy. A real threat would involve difficult decisions about launch windows, asteroid composition, impact geometry, international responsibility, and risk tolerance. But DART moved the subject out of pure theory. Hera will complete the other half of that experiment. DART supplied the impact. Hera supplies the investigation. It will measure the crater, the mass of dimorphos, the internal structure, and the details needed to turn one successful test into a predictive engineering method. Planetary defense is not only about bravery, it is about calibration. The Trojan asteroids, the two large populations of asteroids sharing Jupiter's orbit, clustered at the Lagrange points 60 degrees ahead of and behind Jupiter, are predominantly D-type, among the most primitive and compositionally interesting objects in the solar system. Asteroid taxonomy is useful, but it should not be mistaken for a perfect mineral inventory. A spectrum is a clue, not a sample. Space weathering changes surfaces over time, especially on airless bodies. Solar wind particles, micrometeorite impacts, and radiation darken and redden exposed minerals, sometimes making two objects with similar interiors look different, or two objects with different histories look deceptively similar. A spacecraft visit, a radar observation, a thermal infrared measurement, or a returned sample can revise what a simple, visible light spectrum seemed to imply. This is one reason meteorites matter so much. Meteorites are not anonymous rocks if their mineralogy and oxygen isotope ratios can be linked to asteroid families or parent bodies. Ordinary chondrites connect to S-type asteroids. Carbonaceous chondrites connect to primitive, water-altered bodies. HED meteorites connect to Vesta. Iron meteorites come from metallic cores of differentiated bodies that were broken apart. Every meteorite class is a laboratory doorway into a parent body that may no longer exist as an intact world. The internal structure of asteroids is as diverse as their surface compositions, and understanding it requires looking beyond surface spectroscopy to orbital mechanics, mass measurements, and the occasional spectacular revelation from a close-up spacecraft visit. The simplest asteroid structure is the monolith, a single, coherent piece of rock, intact despite any previous collisions. Monolithic asteroids exist, but may be relatively uncommon among the larger asteroid population, where the scale of prior impacts and the low surface gravity suggest that most large asteroids should have been shattered and reaccreted as loosely bound aggregates. The rubble-pile structure, in which the asteroid is a gravitationally bound aggregate of fragments from previous collisions, held together loosely by self-gravity with essentially no internal strength, is now thought to be the dominant structural type for asteroids larger than a few hundred meters and smaller than perhaps 10 kilometers. The evidence for rubble-pile structure comes from several sources. The rotation rate distribution of larger asteroids shows a maximum spin rate beyond which centrifugal force would overcome self-gravity and shed material from the equator, and virtually no asteroids larger than about 150 meters spin faster than this spin barrier, consistent with the structural constraint of a rubble pile, but not with a solid monolith, which could spin much faster without disrupting. The density of many asteroids measured from spacecraft visits is far lower than the densities of the minerals composing them would imply, again consistent with large internal porosity of a rubble-pile structure. Directly imaged asteroids with rubble-pile structure include Itokawa, visited by the Japanese Hayabusa spacecraft in 2005, which showed a dramatically bilobate shape, reminiscent of Comet 67P, suggesting common formation mechanisms through the gentle merger of two rubble-pile aggregates, with a remarkably smooth surface in some regions and a rough, boulder-covered surface in others. The smooth regions are thought to be deposits of fine regolith that has been shaken down from the boulder-covered regions by seismic vibrations from impacts, avalanching into gravitational lows in the low-gravity environment. At the small end of the size spectrum, asteroids smaller than a few hundred meters can be monolithic shards, small enough to have been produced by a relatively recent fragmentation event and not yet accumulated enough subsequent impacts to form a rubble pile. These small, coherent objects can spin extremely fast, some rotate in minutes, because their tensile strength resists the centrifugal disruption that would shatter a rubble pile at such rotation rates. Binary and multiple asteroid systems add another dimension to structural diversity. A significant fraction of near-Earth asteroids, roughly 15%, have moons, and binary systems are also common in the main belt. Binary formation mechanisms include the YRP effect, the thermal radiation pressure from an irregularly shaped, asymmetrically heated rotating body, which can gradually accelerate or decelerate its rotation until it reaches the spin barrier and begins shedding material from the equator, with the shed material accumulating in orbit to form a satellite. The DART mission in 2022, discussed later, specifically targeted a binary asteroid system. At the opposite extreme from rubble piles, the metallic M-type asteroids and the large differentiated objects like Vesta have coherent internal structure reminiscent of planetary interiors, core, mantle, and crust in the case of Vesta, or a predominantly metallic solid body in the case of the M-types. These are the asteroids that experienced planetary scale processing in the early solar system, and their present-day structure preserves the record of that processing. The rubble pile idea has changed the emotional image of asteroids. A hazardous asteroid is not always a single giant bullet. It may be a gravitationally gathered collection of fragments, with void spaces, boulders, ponds of regolith, weak cohesion, and internal structures that are difficult to predict from a telescope image. This matters for science, and it matters for planetary defense. A kinetic impactor striking a coherent monolith behaves differently from the same impactor striking a porous aggregate. The crater, ejecta, momentum transfer, and post-impact shape change all depend on the hidden interior. Bennu and Ryugu made this lesson vivid. From a distance, they looked like small diamond-shaped worlds. Up close, they were boulder fields, dark and rough, with surfaces far less solid than their silhouettes suggested. Bennu in particular surprised the OSIRIS-REx team because the surface at the sampling site behaved more like a loosely packed granular medium than a firm crust. The spacecraft did not bounce off a hard surface. It pushed in. That one moment revealed something about small asteroids that no remote observation could have shown as clearly. Density is one of the most revealing measurements in asteroid science because it connects surface appearance to hidden interior. If an asteroid size is known from imaging or thermal measurements, and its mass is known from spacecraft tracking, satellite orbits, or gravitational perturbations, then its bulk density can be calculated. Compare that bulk density with the density of the minerals expected from spectroscopy, and the difference reveals porosity. A rocky asteroid with the mineral density of ordinary chondrite material should be much denser than water. If its measured bulk density is far lower, the missing mass is not mysterious material, it is empty space. The asteroid is full of voids. Porosity affects everything. It affects how a crater forms, how seismic waves move, how heat travels, how easily the surface sheds dust, and how a deflection attempt would transfer momentum. A high-porosity asteroid can absorb impact energy differently from a compact one. Its surface may swallow a spacecraft sampling head, as Bennu partly did. Its internal structure may damp seismic shaking or redirect it in unexpected ways. The asteroid's danger, science value, and engineering behavior all depend on this hidden architecture. This is why Hera's measurements at Dimorphos matter. It is not enough to know that DART changed the orbit. Scientists need to know what kind of object was struck. Was it cohesive? Porous? Rubble-pile? Layered? How large was the crater? How much mass was ejected? Without those details, DART is a success story. With those details, it becomes a calibrated method. The largest body in the asteroid belt, and the only one classified as a dwarf planet, is Ceres, with a diameter of about 945 kilometers. Ceres contains roughly 30% of the total mass of the asteroid belt, reflecting how top-heavy the mass distribution is. A few large bodies contain most of the mass, while the vast numbers of smaller asteroids collectively represent a small fraction. Ceres was discovered in 1801 by Giuseppe Piazzi, who was actually attempting to follow up on a predicted position for a planet between Mars and Jupiter suggested by the Titius-Bode relation, an empirical pattern in the spacing of planetary orbits that had suggested a missing planet in the Mars-Jupiter gap. Piazzi found Ceres approximately where predicted, but it was clearly far smaller than any known planet, and subsequent discoveries of additional small bodies in the same region established that the Mars-Jupiter gap contained not one planet, but a population of smaller bodies, the asteroid belt. The spacecraft era of asteroid exploration began slowly, almost accidentally, and then accelerated into one of the most productive branches of planetary science. The first asteroid visited by spacecraft was 951 Gaspra, encountered by Galileo in 1991 on its way to Jupiter. The flyby revealed an irregular, cratered S-type asteroid roughly 19 kilometers long, confirming that small asteroids could be shaped by cratering, fracturing, and regolith processes in ways visible even during a brief encounter. 2 years later, Galileo flew by 243 Ida and discovered Dactyl, the first confirmed moon of an asteroid. That discovery changed assumptions immediately. Asteroids were not always solitary. Even modest-sized bodies could have satellites, opening an entire field of binary asteroid dynamics. The Near-Shoemaker mission brought the next major step. It orbited 433 Eros, a near-Earth S-type asteroid, in 2000, and then made a controlled landing on its surface in 2001, becoming the first spacecraft to orbit and land on an asteroid. Eros turned out to be a heavily cratered, elongated body with grooves, boulders, smooth ponds of regolith, and evidence of surface processes driven by seismic shaking and low gravity. NEAR showed that an asteroid could be studied as a geological world, not merely as a point of light. Japan's Hayabusa mission to Itokawa pushed the field into sample return, even after a mission full of technical crises. Itokawa was tiny, only a few hundred meters across, and looked nothing like a solid rock. It was a contact binary rubble pile, covered in boulders, with smooth regolith-filled areas in gravitational lows. Hayabusa returned only a very small amount of material to Earth in 2010, but those grains were enough to confirm the link between S-type asteroids and ordinary chondrite meteorites. That result solved a long-standing puzzle: why the spectra of S-type asteroids did not perfectly match ordinary chondrites. Space weathering had altered asteroid surfaces, reddening and darkening them. Once that effect was understood, the connection became clear. Each mission changed the mental picture. Gaspra and Ida showed irregular cratered bodies. Eros showed geological complexity. Itokawa revealed rubble piles. Dawn revealed differentiated worlds. Hayabusa 2 and OSIRIS-REx revealed carbon-rich sample chemistry. DART revealed that a spacecraft could change an asteroid's motion. Psyche and Lucy are now extending the story into metallic bodies and Trojan populations. The history of asteroid missions is a history of every close-up view making asteroids stranger, not simpler. The Dawn spacecraft, the first mission designed specifically to orbit bodies in the asteroid belt, visited both Vesta and Ceres, arriving at Vesta in 2011 and Ceres in 2015, and providing the first detailed global characterizations of both. Dawn's observations of Vesta revealed a world shaped by two enormous impact basins at its south pole, Rhea Silvia and Venenia, the former of which is approximately 500 kilometers in diameter, so large relative to Vesta's overall size that the impact must have nearly shattered the entire body. The material excavated from these basins was scattered across the solar system and represents the V-type asteroid family that populates Vesta's orbital neighborhood. Dawn's arrival at Ceres revealed a world quite different from Vesta, more ancient, more primitive, and more physically surprising. Images from Dawn showed Ceres to be a roughly spherical body with a generally cratered, gray surface punctuated by a remarkable feature: bright spots, spectacularly visible in early approach images as bright patches standing out dramatically against the dark surrounding terrain. The brightest of these, in the crater Acator, appeared almost impossibly bright, reflecting far more light than the surrounding surface. The bright spots proved to be deposits of sodium carbonate and ammonium chloride, salts that formed when briny water, welling up from a subsurface reservoir, evaporated in the low-pressure environment of Ceres' surface and left behind crystalline mineral deposits. The implications were profound. Ceres has liquid water, or at least briny salty water, in its interior, rising to the surface through conduits in the crust, probably driven by the slight geological activity still occurring in the aftermath of Ceres' earlier, more active geological history. Ceres is not a cold, dead rock, but a world with ongoing geological, or at least chemical activity, with a subsurface environment that may contain liquid brine today. The Dawn data also revealed a bulk composition for Ceres quite different from the inner rocky asteroids. Ceres has a density substantially lower than any rocky mineral, indicating significant water content, possibly including a layer of ice or a water-rich mantle beneath its surface. The idea that the asteroid belt contains a world, Ceres, with a substantial water inventory was unexpected but is now well supported, and Ceres has been added to the list of solar system bodies potentially harboring conditions relevant to astrobiology. Ceres is especially important because it sits near the boundary between asteroid science and dwarf planet science. It is large enough for gravity to pull it into a nearly round shape, large enough to have separated internally, and water-rich enough that its evolution includes chemistry more familiar from icy moons than from dry inner-belt asteroids. Achater's bright deposits are not decoration. They are evidence that briny material reached the surface geologically recently, leaving salts behind after the water component escaped or froze. Ceres also has Ahana Mons, a solitary mountain interpreted by many researchers as a cryovolcanic dome, a structure formed not by molten rock, but by the movement of icy or briny material from the interior. If this interpretation is right, then Ceres was not simply modified by impacts and left inert. It had internal mobility, chemical gradients, and a water-rich crust capable of slow geological expression. That does not mean Ceres is inhabited, or even that it was ever truly habitable in the strong biological sense. But it does mean the largest asteroid belt body is not a simple rock. It is a water-bearing world. The second target of the Dawn mission, Vesta, is the third largest asteroid at about 525 kilometers in mean diameter. Unlike Ceres, Vesta is one of the most extensively studied asteroids from Earth because the HED meteorites, found in abundance in meteorite collections worldwide, provide direct samples of Vesta's interior and crust for laboratory analysis. Dawn's global mapping of Vesta confirmed what meteorite studies had implied. Vesta underwent significant differentiation early in its history, developing a metallic iron-nickel core, a rocky mantle dominated by olivine and pyroxene, and a basaltic volcanic crust formed by large-scale melting and volcanic eruption approximately 4.5 to 4.55 billion years ago. The heat source for this early melting was the decay of short-lived radioactive isotopes, specifically aluminium-26, which has a half-life of only about 730,000 years and was abundant in the solar system's first few million years after formation from the materials of a supernova. Objects that formed early enough, while aluminium-26 was still abundant, could be significantly heated by its decay. Objects that formed later, after aluminium-26 had largely decayed, experienced less heating and remained more primitive. Vesta's basaltic crust is directly analogous to the basaltic crusts of the terrestrial planets. It formed by the same process of partial melting and volcanic eruption, just on a much smaller body. The geochemical analysis of the HED meteorites has yielded detailed information about the volcanic history of Vesta, the composition of its mantle, and the conditions in the early solar system that produced the radioactive heating. In a very real sense, studying Vesta's meteorites is studying a sample of how planetary volcanic crusts form, in a body small enough to have been geologically disrupted and sampled in ways that large planets cannot be. The enormous southern polar impact basins that dominate Vesta's southern hemisphere are among the most dramatic features in the asteroid belt. The Rhea Silvia Basin, about 500 kilometers across, is so large that its central peak, a mountain rising about 22 kilometers above the basin floor, is one of the tallest mountains in the solar system, comparable in height to Olympus Mons on Mars, but formed by a completely different process. The upward rebound of the basin floor during the impact rather than volcanic accumulation. The scale of the impacts that produced these basins, and the fact that Vesta survived them at all, speaks to the robustness of a differentiated body compared to an undifferentiated rubble pile. The coherent, strong structure of a world with a metallic core and solid rock mantle is considerably harder to shatter than a loosely bound aggregate. The contrast between Ceres and Vesta is one of the most elegant comparisons in planetary science. Ceres is dark, water-rich, salt-bearing, and chemically primitive in important ways. Vesta is dry, basaltic, differentiated, and volcanic. They occupy the same broad region of the solar system, yet they preserve almost opposite histories. One records water alteration and brine chemistry. The other records melting, magma, crust formation, and giant impacts. Together, they show that the asteroid belt is not a collection of identical leftovers. It is a museum of different planetary futures that were interrupted. Ceres might have become something closer to an icy dwarf planet. Vesta became a miniature rocky planet, and then was battered open. Other parent bodies melted completely, formed metal cores, and were later shattered so thoroughly that only iron meteorites remain as their surviving evidence. The planets are the few bodies that finish growing. The asteroids are the many bodies that reveal what finishing growth required. The Psyche mission deserves special attention because asteroid Psyche is not just another small rocky body. It may be a partial exposed core, or it may be a more complex metal-rich world with a mixed origin. Either possibility is scientifically valuable. If Psyche is largely the metallic core of a disrupted protoplanet, then it offers the closest thing we may ever have to a direct look at a planetary core. Earth's core lies beneath thousands of kilometers of mantle and crust, inaccessible except through seismic waves, magnetic field studies, and high-pressure experiments. Psyche, by contrast, may be core-like material exposed to space, preserving the record of differentiation and disruption. Studying it could help explain how small planetary bodies separated metal from silicate, how their cores cooled, and how collisions stripped away outer layers. But Psyche may not be a clean naked core. More recent interpretations allow a more complicated object. Metal-rich, yes, but perhaps mixed with silicates, impact debris, or material altered by billions of years of collisions. That would not make the mission less interesting. It would make it more realistic. The early solar system did not produce perfect textbook objects. It produced partially melted bodies, shattered bodies, reaccreted bodies, and fragments with histories layered on top of one another. Psyche may reveal not a simple core, but the messy aftermath of proto-planetary violence. NASA's Psyche spacecraft, launched in October 2023, is scheduled to be captured by the asteroid's gravity in 2029 and begin its prime mission soon after. It carries instruments to measure Psyche's composition, topography, magnetic properties, and gravity field. If Psyche retains remnant magnetization, that could suggest it once cooled in the presence of a magnetic field generated by a dynamo in its parent body's molten core. Such a result would be extraordinary, a small metallic asteroid preserving the magnetic memory of a vanished protoplanet. The asteroid families, groups of asteroids sharing similar orbital parameters and spectral properties, are the debris fields left by past collisions between major asteroids, and they are among the most direct records of the belt's violent collisional history. When a large asteroid is struck by a smaller but still substantial impactor, the collision can fragment or cratering both parent body, scattering debris into orbital paths broadly similar to the original asteroid's orbit, but with slightly different semi-major axes, eccentricities, and inclinations. The scattered fragments form a family of asteroids, closely related in orbital parameters and surface composition, drifting apart over millions of years as subtle gravitational and radiation effects slowly spread the family members through orbital space. The Vesta family, produced by the Rhea Silvia and Venenia impacts, is the most famous and best studied, with thousands of confirmed V-type asteroids occupying orbits consistent with ejection from Vesta's south pole. The dynamical analysis of the Vesta family distribution across orbital space can be reversed in time by modeling the gradual orbital evolution of each family member under gravitational perturbations and the Yarkovsky effect. See below. The distribution of family members can be traced back to a more concentrated initial cluster, allowing the age of the impact event to be estimated. The Rhea Silvia impact is dated to roughly 1 billion years ago by this method, while Venonea appears to be older, perhaps 2 billion years. The Themis family is a large C-type family in the outer belt, associated with the disruption of an ancient, water-bearing parent body. Some members of the Themis family show evidence of water ice or hydrated minerals on their surfaces, and the Themis family is thought to represent fragments of an outer belt body that had incorporated significant water ice in its formation. The discovery of main belt comets, active asteroids showing cometary activity, within the Themis family region supports the idea that water-bearing material, possibly including ice, exists within some Themis family members. The Caronis family is a prominent S-type family in the middle belt, and individual members of this family were among the first asteroids to have their rotation states studied in detail. The discovery that many Caronis family members have spun up or spun down to cluster at two specific rotation periods, rather than showing the expected continuous distribution of periods, revealed the YRP effect operating in the solar system for the first time. These asteroids have had their rotation rates systematically modified by asymmetric thermal emission over the family's 1 to 2 billion year history. Asteroid families also let scientists date collisions in a way that feels almost like forensic astronomy. A family starts compact. Fragments leave the parent body at different speeds, but they initially occupy a related set of orbits. Over time, gravitational perturbations, resonances, and thermal forces spread them out. By modeling that spreading backwards, researchers can estimate when the original collision happened. This is not simple, and it is not exact, but it turns the current distribution of fragments into a clock. Some families are ancient enough that their edges have blurred. Others are young and crisp. A very young family can preserve fresh surfaces that have not yet been strongly altered by space weathering. A very old family shows how billions of years of small forces reshape orbits. The belt is not static. Even when nothing seems to be moving in a human lifetime, it is dynamically alive on geological timescales. The Yarkovsky effect and the YRP effect are subtle but enormously important processes that govern the long-term orbital evolution of asteroids and directly connect to the question of which asteroids may eventually approach Earth. The Yarkovsky effect is a tiny force produced by the asymmetric re-radiation of solar heat from a rotating asteroid. When sunlight heats an asteroid's surface, the warmer sunlit side radiates more heat than the cooler night side, and this asymmetric radiation creates a net force on the asteroid. For a prograde rotating asteroid, one that spins in the same direction as its orbital motion, the force pushes slightly in the direction of orbital motion, slowly increasing the orbital energy and expanding the orbit over time. For a retrograde rotating asteroid, spinning in the opposite direction, the force acts slightly against the orbital direction, contracting the orbit. The Yarkovsky effect is tiny, accelerations of roughly 100 millionths to 100 billionths of a standard gravity, but integrated over millions to billions of years, it can shift an asteroid's orbital radius by a significant fraction of an astronomical unit, potentially delivering it to a mean motion resonance with Jupiter or a secular resonance with Saturn that then dramatically increases its orbital eccentricity, potentially crossing the orbits of the inner planets. The YRP effect, Yarkovsky-O'Keefe-Radzievsky-Paddock, is a related phenomenon, the asymmetric thermal radiation from a rotating, irregularly shaped asteroid produces not only a linear force, the Yarkovsky effect, but also a torque, which can systematically accelerate or decelerate the asteroid's rotation. Over geological timescales, YRP can spin up a rubble pile to the point where it reaches the spin barrier and begins shedding material, potentially forming a binary asteroid or a top-shaped equatorial bulge, a morphology seen in several well-studied near-Earth asteroids, including Bennu and Ryugu. The combination of the Yarkovsky effect delivering asteroids to resonances, and those resonances pumping up orbital eccentricities until the orbits cross those of the terrestrial planets, is the primary mechanism by which asteroids are transported from the main belt into the near-Earth population. This is an ongoing process. Main belt asteroids continue to be delivered to the near-Earth region at a rate that roughly balances the rate at which near-Earth asteroids are removed by impacts on the Sun, on the planets, or by ejection from the solar system. The importance of these effects is easy to underestimate because they are so small. But small forces are exactly what matter over the age of the solar system. A push too slight to notice in one orbit becomes decisive over millions of orbits. A thermal imbalance that could not move a mountain in a day can move a kilometer-scale asteroid into a resonance over geological time. Once an asteroid reaches the resonance, the gentle part of its journey ends. Jupiter or Saturn can then pump up the eccentricity of the orbit, sending the body inward toward Mars, Earth, Venus, or the Sun. This is the delivery system for many meteorites. A rock is broken from its parent body in the main belt. It spends millions of years exposed to cosmic rays as a small fragment. Thermal forces slowly shift its orbit. A resonance takes over. The fragment becomes an Earth-crossing object. Then, on one particular day, it enters the atmosphere as a fireball. By measuring its cosmic ray exposure age and its mineral chemistry, scientists can reconstruct parts of that journey. The near-Earth asteroids, those with orbits that bring them within 1.3 astronomical units of the Sun, potentially crossing or approaching Earth's orbit, are the population of most immediate practical concern for planetary defense, and also the most easily reached targets for spacecraft missions. Near-Earth asteroids are classified by their orbital characteristics relative to Earth's orbit. More asteroids have orbits that cross Mars's orbit but do not currently cross Earth's orbit. Apollo asteroids cross Earth's orbit with semi-major axes larger than Earth's. Aten asteroids have semi-major axes smaller than Earth's and orbits that still cross Earth's. In a fourth class, the Asteroids or Apophis have orbits entirely within Earth's orbit. The classification affects the specific dynamical hazard each type presents, but all are monitored for potential close approaches to Earth. The current catalog of known near-Earth asteroids has now passed 40,000 confirmed objects, with thousands designated as potentially hazardous, meaning, in the standard definition, objects at least about 140 meters across whose orbits can bring them within about 7.5 million kilometers of Earth's orbit. The phrase potentially hazardous does not mean an impact is expected. For most known potentially hazardous asteroids, detailed orbital calculations confirm that they pose no impact risk in the foreseeable future, and the catalog grows continuously as survey programs discover new objects and refine the orbits of previously known ones. The most capable survey programs include the Catalina Sky Survey in Arizona, the Panoramic Survey Telescope and Rapid Response System, or PANSTARRS, in Hawaii, and the Atlas Survey, which was designed specifically to provide early warning for small impactors. Together, these programs discover new near-Earth asteroids continuously, systematically surveying the sky and combining new discoveries with follow-up observations to refine orbital solutions. The Vera C. Rubin Observatory has now begun the legacy survey of space and time, turning its large aperture, wide field of view, and rapid cadence into the most powerful solar system discovery machine ever built. In parallel, NASA's NEO Surveyor mission, targeted for launch no earlier than September 2027, will search in infrared from space, improving the census of dark asteroids and objects approaching from directions difficult for ground-based telescopes, including regions closer to the Sun in the sky. A handful of near-Earth asteroids have been designated as requiring special attention, either because their orbital uncertainties are large enough that an impact cannot be ruled out, or because their current best-fit orbit comes uncomfortably close to Earth at some future date. Apophis, a roughly 370-meter asteroid discovered in 2004, caused significant concern when initial orbital calculations suggested a small but non-trivial probability of impact in 2029. Further observations refined the orbit and removed the 2029 impact possibility, but Apophis will make an exceptionally close approach in April 2029, passing within about 37,000 kilometers of Earth, inside the orbits of geostationary satellites. This close approach will be directly observable with the naked eye from Europe, Africa, and Western Asia as a point of light moving rapidly across the sky over the course of several hours, and will be observed by multiple ground-based and space-based instruments. The 2029 flyby will also modify Apophis's orbit and may alter its rotation or surface in ways that depend on the asteroid's internal structure and composition. That does not mean Apophis is expected to hit Earth afterward. Current calculations rule out impact risk for at least the next century, but it does mean the encounter will be a rare natural experiment in how a close planetary flyby reshapes a small body. Apophis is an excellent example of how planetary defense has matured from fear into measurement. When Apophis was discovered in 2004, early calculations briefly allowed a small possibility of impact in 2029. That possibility was frightening because the asteroid is large enough, roughly a few hundred meters across, to cause severe regional or even broader consequences if it struck Earth. But early orbits are uncertain. As more observations came in, the impact possibility for 2029 disappeared. Later observations also ruled out impacts for the following close approach opportunities within the foreseeable planning horizon. The story of Apophis is therefore not a story of an asteroid that nearly hit Earth. It is a story of how orbit determination improves with data. The 2029 flyby remains scientifically extraordinary. On April 13, 2029, Apophis will pass closer to Earth's surface than many high-altitude satellites, close enough that Earth's gravity will alter its orbit and may change its spin state or disturb its surface. It will be visible to many observers on Earth as a moving point of light. Events like this are rare on human timescales. A large asteroid passing safely, predictably, and close enough to study in detail. The OSIRIS-REx spacecraft, after delivering its Bennu sample to Earth, was renamed OSIRIS-APEX and sent onward to study Apophis after the 2029 encounter. That mission will turn a once-feared asteroid into a laboratory for close planetary encounters. By comparing Apophis before and after Earth's tidal influence, scientists may learn how close flybys reshape small bodies, move regolith, trigger landslides, and modify rotation. The same gravitational physics that once made Apophis alarming now makes it scientifically useful. Bennu, the target of the OSIRIS-REx mission, is a relatively small, about 500 meters, but carbon-rich near-Earth asteroid that currently has a small cumulative probability of impacting Earth in the 22nd century, with the highest probability individual impact opportunity in 2182. The OSIRIS-REx mission was motivated in part by the scientific value of a carbonaceous near-Earth asteroid sample return, but also by the practical need to improve orbital predictions for Bennu, and the precise measurement of Bennu's trajectory by OSIRIS-REx has refined the impact probability estimates substantially. There is a subtle psychological mistake in planetary defense. People often imagine the danger as one famous asteroid with a name and a date. In reality, the main defense problem is statistical. Most of the kilometer-scale objects have been found, and none is known to threaten Earth in the next century. The remaining work is the smaller population, objects large enough to destroy a city or region, but small enough and dark enough that many remain undiscovered. The Chelyabinsk object was only about 20 meters across, yet it injured more than 1,000 people because of the shockwave from its airburst. A 140-meter asteroid is not a dinosaur killer, but it is large enough to cause regional catastrophe. This is why survey completeness matters more than dramatic headlines. Planetary defense begins with discovery, not with deflection. You cannot change the orbit of an asteroid you have not found. Once an object is discovered early enough, even a small change in velocity can become a large missed distance years later. If it is discovered too late, options shrink quickly. NEO Surveyor and Rubin represent two complementary answers to the same problem. Rubin is a wide, deep, repeated survey of the sky from the ground. It will find enormous numbers of moving objects by returning to the same regions again and again, building orbits from repeated detections. It is powerful because of its cadence, camera size, depth, and sky coverage. It will discover main belt asteroids, near-Earth objects, Trojans, trans-Neptunian objects, comets, interstellar candidates, and small bodies in categories that may not yet be well represented in catalogs. In its early optimization surveys alone, Rubin already began showing how quickly it can reveal previously unknown solar system objects. NEO Surveyor is different. It is designed specifically for planetary defense and will observe in infrared. Infrared matters because asteroids shine thermally according to their size and temperature, not only according to how much sunlight they reflect. A dark asteroid and a bright asteroid of the same size can look very different in visible light, but infrared observations help measure size more directly. This is crucial because hazard depends on size and mass, not brightness. A small bright asteroid can look deceptively important. A large dark asteroid can look deceptively faint. Together, ground-based optical surveys and space-based infrared surveys can do what neither can do alone. They can find more objects, measure them better, and reduce the blind spots imposed by daylight, weather, the moon, telescope latitude, and the glare of the sun. The OSIRIS-REx mission to Bennu and the Japanese Hayabusa 2 mission to Ryugu are the two most scientifically significant asteroid sample return missions yet completed, and their results have transformed understanding of carbonaceous asteroid composition. Hayabusa 2 launched in December 2014, arrived at Ryugu in June 2018, spent about 18 months studying the asteroid in detail and collecting samples, then departed in November 2019 and released a sample return capsule that landed in the South Australian desert in December 2020. The capsule contained about 5.4 grams of material from Ryugu's surface, small by human standards, but scientifically enormous. A clean, well-documented sample from a known carbonaceous asteroid, protected from most of the contamination uncertainties that complicate meteorites collected after falling to Earth. Ryugu is a C-type asteroid with a distinctive top-shaped morphology, an equatorial ridge suggesting that the YLRP effect has spun the object up enough to flatten it and accumulate a bulge of material around its equator. Its surface is covered in boulders and has a very low albedo, consistent with carbon-rich material. Initial spectroscopic observations from Hayabusa 2 showed features consistent with hydrated minerals, silicates that have incorporated water into their crystal structure, suggesting that Ryugu's parent body experienced liquid water chemistry at some point in its history. The laboratory analysis of the returned samples confirmed and dramatically extended these initial observations. Ryugu's material proved to be dark, carbon-rich, chemically primitive, and permeated with complex organic molecules, with hydrated minerals confirming that liquid water processed the original asteroid material. Early analyses detected important nitrogen-bearing organic molecules, including uracil, and later analyses reported all 5 of the nucleobases used in terrestrial DNA and RNA: adenine, guanine, cytosine, thymine, and uracil, in Ryugu's material, along with a broader inventory of amino acids and other organically significant molecules. The detection of all 5 DNA and RNA nucleobases in an asteroid sample was a landmark result. Combined with earlier detections of nucleobases in carbonaceous meteorites, it confirms that these specific molecules, the information-carrying monomers of biology, can be produced abiotically through the chemistry occurring within asteroid parent bodies and can survive through impacts and deliveries to planetary surfaces. The prebiotic chemistry of the early Earth was almost certainly enriched by this kind of impactor-delivered molecular inventory, potentially including the specific molecules that ended up forming the first nucleic acids. OSIRIS-REx launched in September 2016, arrived at Bennu in December 2018, spent about 2 years studying and mapping the asteroid before attempting sample collection in October 2020, and returned a sample capsule to Earth in September 2023 containing 121.6 grams of material from Bennu's surface. Initial analysis of the material revealed dark, carbon-rich, hydrated material broadly similar in character to Ryugu's samples. Both asteroids appear to be fragments of ancient carbonaceous parent bodies that experienced significant aqueous alteration. Detailed analysis of the Bennu samples has been ongoing since return, with results being published over several years. One interesting difference between Bennu and Ryugu is their surface properties. Bennu, despite being a rubble-pile like Ryugu, surprised mission scientists with its loose, low-cohesion surface. When the OSIRIS-REx spacecraft touched down for sample collection, its mechanism contacted a surface that was so loosely consolidated that the spacecraft began to sink into it, and the sample collected turned out to be much larger than anticipated, with the spacecraft's collection chamber overflowing and material being lost before the chamber could be fully sealed. The looseness of Bennu's surface suggests that many small asteroids may be far less cohesive and solid than their appearance suggests, a factor with important implications for deflection strategies. The returned samples are a major reason asteroid science has entered a new phase. A telescope can measure color and brightness. A spacecraft can map shape and surface composition. But a returned sample can be taken apart atom by atom. It can be examined for isotopes, amino acids, nucleobases, salts, minerals formed in liquid water, tiny grains older than the Sun, and contamination controls strict enough to separate original asteroid chemistry from anything introduced on Earth. The Bennu sample has been especially important because it contains volatile-rich, carbon-rich material with ammonia, soluble organic compounds, amino acids, and the canonical nucleobases used by DNA and RNA. This does not mean Bennu contained life. It means the chemical ingredients associated with life can form in small water-altered bodies without biology. That distinction is crucial. Asteroids may not have delivered life to Earth, but they almost certainly help deliver part of the chemical inventory from which prebiotic chemistry could work. The Bennu and Ryugu samples also changed the tone of discussions about life's ingredients. For many years, the idea that asteroids delivered prebiotic molecules to Earth was plausible, but partly dependent on meteorites that had fallen through Earth's atmosphere, landed on the surface, and then been exposed to terrestrial contamination. Meteorites can be extraordinarily well studied, and contamination controls are sophisticated, but a sample collected directly from a known asteroid and sealed for return carries a different level of confidence. Hayabusa 2 and OSIRIS-REx delivered material whose history from asteroid surface to laboratory was controlled and documented. The result is not that life came from asteroids. That would be far too strong. The result is that asteroids carried a rich inventory of the kinds of molecules from which prebiotic chemistry can draw: amino acids, nucleobases, ammonia, salts from ancient briny environments, hydrated minerals formed in the presence of water. These objects were not biologically alive, but chemically fertile. They show that the early solar system did not need life in order to make life-relevant chemistry. This matters for Earth because the young planet was not chemically isolated. It grew by impacts. It was struck by carbon-rich bodies. Its oceans and atmosphere evolved under the influence of material delivered from beyond the inner solar system. Whether the exact molecules delivered by asteroids became part of the pathway to life is still unknown, but the delivery mechanism is real and the inventory is real. Asteroids help bridge the gap between planetary formation and prebiotic chemistry. The story is also not finished because sample analysis takes decades. Apollo lunar samples are still producing new science more than half a century after they were collected because instruments improved and new questions emerged. Bennu and Ryugu samples will be the same. Some material is examined immediately. Some is sealed for future generations, who will have instruments more sensitive than ours and questions we have not yet learned to ask. A return sample is therefore not only a scientific result, it is a scientific reserve. This is one of the quiet strengths of sample return missions. A spacecraft flyby is brief. An orbiter lasts years if it is fortunate, but a sample in a clean laboratory can be studied again and again, with new methods, by scientists not yet born when the mission launched. Asteroid material returned now becomes a resource for future science in the same way meteorites have been, but with a known parent body and a known collection context. The deflection of potentially hazardous asteroids, changing their orbits enough to prevent a future impact, is a genuine and practically important area of planetary defense, and it moved from theoretical discussion to direct demonstration in September 2022 with the DART mission. The Double Asteroid Redirection Test, or DART, was specifically designed to test the kinetic impactor technique, crashing a spacecraft into an asteroid at high velocity and measuring the change in orbital period that results from the momentum transferred by the impact. The target was Dimorphos, the roughly 160-meter moon of the larger asteroid Didymos, chosen because the binary system geometry allowed the change in Dimorphos's orbit around Didymos to be measured precisely from Earth-based telescopes by tracking how the timing of Dimorphos's eclipses of Didymos changed. DART impacted Dimorphos on September 26, 2022, at approximately 6.1 kilometers per second. The impact was observed in real time by DART's own camera and by the Italian LIC IA-Cube spacecraft, which had separated from DART about 2 weeks earlier and flew past Dimorphos about 3 minutes after the impact, transmitting images of the ejecta cloud. Earth-based and space-based telescopes then monitored the system for weeks to months, measuring the change in Dimorphos's orbital period around Didymos. The result exceeded expectations. Pre-impact models predicted a period change of about 7 minutes if the impact simply transferred the spacecraft's momentum to the asteroid, as if it were a billiard ball collision. The actual measured period change was about 33 minutes, roughly 4 to 5 times the minimum expected. The reason for the amplification is the ejecta. The impact excavated an enormous amount of material from Dimorphos's surface, and as this material was ejected into space in a roughly coherent direction opposite to the impact direction, the reaction force of that ejection pushed Dimorphos in the same direction as the spacecraft's momentum. amplifying the total momentum change far beyond what the spacecraft's mass alone would have provided. This ejecta amplification is called the momentum transfer enhancement factor, or beta, and knowing its typical value is crucial for planning future kinetic impactor missions for planetary defense. The DART result confirmed that the ejecta contribution can be very significant, by a factor of roughly 4 to 5 in the case of Dimorphos, which means that kinetic impactors can deflect asteroids using much smaller spacecraft than would be required if only the spacecraft's momentum counted. This is reassuring from a practical standpoint. A kinetic impactor mission targeting a real threatening asteroid could achieve the required deflection with a manageable spacecraft mass even for substantial asteroids. The ESA Hera mission, launched in October 2024, is en route to the Didymos system and is expected to reach it in late 2026. Hera will carry out detailed follow-up observations of Dimorphos, measure the crater or surface change left by DART, characterize the moonlet's mass and internal structure, and turn the DART impact from a successful demonstration into a calibrated planetary defense experiment. There is a quiet institutional story behind planetary defense that rarely appears in dramatic accounts. A threatening asteroid would not be handled by one telescope or one country alone. Discovery observations are reported to the Minor Planet Center, where positions are collected and orbits begin to be calculated. NASA's Center for Near-Earth Object Studies and ESA's Near-Earth Object Coordination Center independently monitor close approaches and impact probabilities. The International Asteroid Warning Network helps coordinate observations and communication if a credible threat is found. The Space Mission Planning Advisory Group exists to discuss possible space mission responses if deflection or reconnaissance becomes necessary. This matters because an impact prediction is not merely a scientific result. It is a public event. It affects governments, risk communication, evacuation planning, international law, and trust. A small impactor might require local warnings. A larger object might require years of international coordination. A deflection mission could slightly change where risk falls on Earth during the process of moving the impact corridor away from the planet. Planetary defense is therefore both astronomy and governance. The Sky Survey is the beginning, not the whole response. Beyond kinetic impactors, other deflection technologies have been studied. The gravity tractor concept uses a spacecraft flying in formation with an asteroid, never touching it, and using the gravitational attraction between the spacecraft and the asteroid to slowly tug the asteroid into a new orbit over many months or years. This approach requires no physical contact and is independent of the asteroid's surface properties, but requires very long lead times and relatively large spacecraft for meaningful deflection of substantial asteroids. Ion beam deflection is a related concept in which a spacecraft fires an ion beam at the asteroid's surface, ablating material and creating a gentle but sustained thrust. Nuclear deflection, detonating a nuclear device near or on the surface of an asteroid, is the most powerful available technique for very large objects or very short warning times, but carries the risk of fragmenting the asteroid into multiple pieces if not executed correctly. The practical requirement for any deflection mission is warning time. The earlier a potentially threatening asteroid is identified, the less total delta V is required to change its orbit enough to prevent impact, because small orbital changes applied early amplify into large position differences at the time of the potential impact. For asteroids a decade or more before a predicted impact, even a modest kinetic impactor mission could provide the necessary deflection. For asteroids discovered only a year or two before a predicted impact, the deflection challenge becomes far more demanding. Completing the census of potentially hazardous asteroids, finding virtually all of them before they find us, is therefore the highest priority component of planetary defense, and the Vera Rubin Observatory's completion of the survey to smaller sizes over the next decade is a central element of that program. The Trojan asteroids, the populations of small bodies sharing Jupiter's orbit but clustered 60 degrees ahead of and behind the giant planet at the Lagrange points L4 and L5, are one of the most interesting and compositionally distinct populations in the solar system. Jupiter's Trojans number in the hundreds of thousands of objects larger than 1 kilometer, comparable to the main belt in total population, and may represent material captured from a wide range of heliocentric distances during the early solar system's period of giant planet migration, the same orbital reshuffling that characterizes the nice model of early solar system dynamics. Because the Trojans may have been captured from diverse sources, including material originally from the outer solar system, including Kuiper belt-like composition, they may represent a more diverse sampling of early solar system material than the relatively local asteroid belt. The Trojans are predominantly D-type and P-type asteroids, very dark, very red, with spectral features suggesting the presence of complex organic compounds and perhaps primitive silicates. The redness of their surfaces, combined with the primitive compositions inferred from spectroscopy, places them compositionally between the main belt C-types and the Kuiper belt objects, consistent with their possible origin in a variety of source populations captured during planetary migration. NASA's Lucy mission, launched in October 2021, is the first spacecraft designed to study multiple Jupiter Trojans. On its complex 12-year trajectory, Lucy has already used main belt encounters as rehearsals and scientific opportunities. In November 2023, Lucy flew past the small asteroid Dinkinish and revealed a surprisingly complex system. Dinkinish has a small satellite, Salam, and Salam itself is a contact binary made of two lobes touching each other. In April 2025, Lucy flew within roughly 960 kilometers of Donald Johanson, returning close-up images of an elongated, peanut-shaped object with a more complex rotation state than a simple single-axis spin. The Trojan encounters themselves begin in 2027, with targets chosen to sample the diversity of Trojan compositions and sizes, including the binary system Patroclus and Menoetius. Trojan populations are not unique to Jupiter. Mars and Neptune have known Trojans, and Earth has a small number of known co-orbital companions, including Earth Trojans and quasi-satellites. Earth Trojan 2010 TK7 was the first confirmed example, and later discoveries showed that small objects can share Earth's orbit temporarily in complex gravitational arrangements. These co-orbital companions of Earth are generally small and unstable on geological timescales, drifting in and out of stable co-orbital configurations under gravitational perturbations. Saturn, by contrast, does not host a large stable Trojan population comparable to Jupiter's, largely because Jupiter's gravity destabilizes much of the relevant phase space. The Trojans matter because they may preserve material from the era when the giant planets migrated. In many models, Jupiter, Saturn, Uranus, and Neptune did not form exactly where we see them today. Their changing orbits reshuffled small bodies across the outer solar system, scattering some inward, throwing some outward, and trapping some near stable gravitational points. If the Trojans were captured during that reshuffling, they are not just companions of Jupiter. They are witnesses to the moment when the architecture of the outer solar system was rearranged. Lucy's long journey is designed around that idea. By visiting multiple Trojans instead of one, it can test whether these bodies are compositionally uniform or diverse, whether the two Trojan swarms differ, and whether binary systems like Patroclus and Menoetius preserve clues about the low-velocity conditions of early accretion. The mission is slow because the geometry is hard, but the scientific payoff is unusually broad. one spacecraft sampling several different fossils of the giant planet era. Lucy is especially valuable because the Trojan swarms are not a single asteroid. They are populations. One close flyby of one Trojan would be useful, but it could never answer whether Jupiter's Trojans are uniform, diverse, captured from one region, or mixed from several sources. Lucy's design recognizes that the population itself is the target. It will visit several bodies of different sizes, colors, and dynamical groupings, turning a mission trajectory into a comparative survey. The early flyby of Dinkinish in 2023 was already a reminder that small bodies hide surprises. Dinkinish turned out to have a small satellite, later named Salam, and that satellite itself is a contact binary. Instead of a simple small main belt asteroid, Lucy found a miniature multiple system. Then, in April 2025, Lucy flew past Donald Johanson, another main belt target named after the discoverer of the famous Lucy fossil. These encounters were rehearsals before the Trojan science begins in earnest, but they were also real discoveries in their own right. When Lucy reaches the Trojans, the questions will be about color, composition, density, cratering, binary formation, and whether the L4 and L5 swarms preserve different histories. If the Trojans were captured during giant planet migration, their properties may constrain not only asteroid science, but the movement of Jupiter and Saturn themselves. A small dark object near Jupiter can therefore become evidence about the architecture of the entire solar system. The potential economic value of asteroid resources has attracted increasing attention over the past 2 decades, as the combination of growing space capabilities and the recognized abundance of specific materials in different asteroid types has motivated both theoretical and practical exploration of asteroid mining concepts. Metallic M-type and S-type asteroids contain iron, nickel, cobalt, and platinum group metals, the latter including elements like platinum, palladium, rhodium, and iridium that are extraordinarily rare in Earth's crust, but are found in metallic asteroids at concentrations orders of magnitude higher than in the most metal-rich terrestrial or deposits. The theoretical value of the metal content of a single large metal-rich asteroid is often exaggerated in popular articles, sometimes with numbers so large that they sound more like mythology than economics. A calmer scientific point is more useful. Metal-rich asteroids may contain iron, nickel, cobalt, and platinum group elements in concentrations very different from ordinary terrestrial crustal rocks. Whether any of that material could ever be extracted economically depends on launch costs, automation, energy, processing technology, transport, market effects, and law. The existence of metal in space is not the same thing as an accessible mine. More near-term and practically relevant is the possibility of using asteroid resources in space rather than returning them to Earth. Water extracted from carbonaceous asteroids, in the form of ice or hydrated minerals, could be electrolyzed in space to produce hydrogen and oxygen rocket propellant, enabling a significantly reduced cost for deep space missions that could refuel at asteroid depots rather than carrying all their propellant from Earth. This concept, using asteroid water as a space resource rather than returning it to Earth, is considered the most economically plausible first application of asteroid mining, and several private companies have been developing the relevant technologies. The legal and ethical future of asteroid resources will probably be as difficult as the engineering. If water, metals, or other materials are extracted from asteroids, who owns them? A nation cannot claim sovereignty over an asteroid under the Outer Space Treaty, but some national laws recognize ownership of extracted resources. That distinction may sound neat legally, but it becomes complicated when operations scale up. What counts as extraction? What counts as harmful interference with another mission? How close can two operators work around the same small body? Who is responsible if a mining operation changes an asteroid's spin state, sheds debris, or alters an orbit in a way that creates risk? The first asteroid resource missions are likely to be small and scientific or demonstrational rather than industrial. But the legal framework will matter before the economics become large, because space operations require predictability. The asteroid belt is not about to become a mining district tomorrow. Still, the fact that these questions are being asked seriously is itself a sign that asteroids have moved from background objects to future infrastructure in human planning. The regulatory environment for asteroid resource utilization is still being established. The 2015 U.S. Commercial Space Launch Competitiveness Act was the first national legislation to explicitly recognize the rights of U.S. companies to own and sell resources extracted from asteroids. But international law on asteroid resources remains unsettled, with different interpretations of the Outer Space Treaty, which prohibits national appropriation of celestial bodies, but says nothing explicitly about resource extraction by non-governmental entities, leading to varying national legislative approaches. The long-term legal framework for asteroid resource utilization will need international agreement that has not yet been reached. Asteroid mining often suffers from exaggerated framing. It is easy to say that a metallic asteroid contains wealth greater than the entire world economy, but that statement is not the same as an economic plan. Value on Earth depends on scarcity, demand, extraction cost, transport cost, market absorption, and legal control. If an enormous quantity of platinum group metals were suddenly delivered to Earth, the market price would not remain unchanged. The simple multiplication of asteroid mass by current metal prices is therefore misleading. The more realistic near-term value is not treasure returned to Earth, but material used in space. Water is propellant. Water is radiation shielding. Water is life support. Carbonaceous asteroids may someday be useful not because they are glamorous, but because they contain the most practical molecule in space operations. The first economically meaningful asteroid resource may not be platinum. It may be water extracted and split into hydrogen and oxygen, used to move spacecraft without lifting every kilogram from Earth's deep gravity well. The role of asteroids in Earth's geological and biological history extends from the distant past, the heavy bombardment, and its role in delivering water and organics, to the more recent and visible record of impact craters that punctuate Earth's surface. Earth currently has roughly 190 confirmed impact craters, a number that is almost certainly a dramatic underestimate of the true total due to the extensive geological processing, plate tectonics, erosion, volcanic resurfacing, seafloor subduction, that continuously erases the impact record on a geologically active planet like Earth. The Moon, lacking these processes, preserves essentially its complete impact record in its heavily cratered surface, and comparison of the lunar and terrestrial crater databases provides estimates of how many Earth craters have been erased. The story of impact craters on Earth is also a story of erasure. The Moon preserves its scars because it has no atmosphere, no oceans, no plate tectonics, and very little erosion. Earth is different. Rain, rivers, glaciers, wind, volcanism, sedimentation, and subduction erase evidence. Oceanic crust is recycled. Continental crust is deformed. A crater that would remain obvious on the Moon for billions of years can become nearly invisible on Earth in a fraction of that time. This is why the confirmed terrestrial impact crater database is not a complete record of impacts. It is the surviving record after Earth has done everything possible to hide the evidence. Some craters remain dramatic, like Meteor Crater in Arizona. Others are visible only through geophysical mapping, shocked minerals, gravity anomalies, magnetic signatures, or thin chemical layers in sediment. Chicxulub was not discovered as a giant obvious hole in the ground. It was recognized through a chain of evidence: iridium enrichment at the boundary, shocked quartz, spherules, global ejected deposits, and then the buried circular structure beneath the Yucatan. The crater was there, but Earth had covered it. This matters because the asteroid impact story is not only a space story. It is written into geology, climate, extinction, mineral deposits, and biological opportunity. An asteroid changed the direction of evolution 66 million years ago, not because it was large by asteroid belt standards, but because it arrived at Earth at the wrong place, at the wrong speed, at the wrong time, striking rocks rich in sulfur and carbonates and turning a regional impact into a global environmental crisis. The confirmed impact craters range from small, relatively recent features. Meteor crater in Arizona, about 1.2 kilometers in diameter, formed roughly 50,000 years ago by an iron meteorite about 50 meters across, to ancient, deeply eroded structures spanning tens to hundreds of kilometers. The Vredefort Dome in South Africa, about 300 kilometers in diameter and roughly 2 billion years old, is the largest confirmed impact structure on Earth. The Sudbury Basin in Ontario, Canada, roughly 130 kilometers, is another ancient impact structure that preserves the eroded remnant of an impact roughly equivalent in scale to the Chicxulub impact. The Chicxulub structure, buried beneath the Yucatan Peninsula and the Gulf of Mexico, is about 150 to 200 kilometers in diameter and formed 66 million years ago by an impactor approximately 10 to 15 kilometers in diameter. The impact released an amount of energy roughly equivalent to 1 billion nuclear weapons, triggering wildfires, a global dust cloud that blocked sunlight for months, acid rain from sulfur dioxide released from the impacted rock, and a dramatic, sustained cooling of Earth's climate, the impact winter, that ended the Cretaceous period and caused the extinction of approximately 75% of species, including all non-avian dinosaurs. The discovery of the iridium anomaly in Cretaceous-Paleogene boundary sediments worldwide in 1980 by Luis and Walter Alvarez, a globally distributed thin layer enriched in iridium, an element rare in Earth's crust but abundant in certain asteroid types, provided the first compelling evidence for an impact cause of the K-PG extinction, and the subsequent discovery and characterization of the Chicxulub structure confirmed it. The impact extinction of the dinosaurs opened the ecological niches that mammalian life subsequently expanded into, ultimately leading to the evolutionary lineage that produced humans, making the asteroid responsible for the Chicxulub impact, in a very indirect and entirely inadvertent way, a precondition for human existence. Smaller impacts continue to occur, and the terrestrial impact flux, the rate at which asteroids of various sizes strike Earth, has been estimated from crater counting, from historical records, and from observations of fireballs and meteorite falls. Objects a meter or smaller enter Earth's atmosphere several times per year, producing brilliant fireballs but burning up before reaching the surface. Objects a few meters across produce superbolide fireballs with energies comparable to small nuclear weapons but typically detonate in the upper atmosphere, as the Chelyabinsk event of February 2013 demonstrated dramatically. The Chelyabinsk superbolide, an asteroid approximately 20 meters in diameter, entered the atmosphere over Russia's Ural region and exploded at an altitude of about 23 kilometers, releasing an energy of roughly 500 kilotons TNT equivalent, about 30 times the Hiroshima bomb. The shockwave shattered windows across a wide area and injured roughly 1,500 people, none fatally. Crucially, the Chelyabinsk object was not detected in advance. It came from the direction of the sun and was missed entirely by existing survey programs until it entered the atmosphere. The asteroid hazard is often misunderstood because size changes everything. A 1-meter object is mostly a This is why the boundary between inert and active is no longer simple. An object can look asteroidal for most of its orbit and then briefly release dust. Another can have a meteor shower associated with it. Another can preserve hydrated minerals from ancient water while being dry today. The small body population is not divided into dead rocks and icy comets, as cleanly as older textbooks suggested. It is a continuum of material, temperature, volatile content, orbit, and history. And there is a human reason the subject matters. For most of history, impacts were invisible as a cosmic process. A crater was just a circular lake, a strange depression, a mythic landscape, or a local geological curiosity. Meteorites were stones that fell from the sky, often doubted by scholars until the evidence became too strong to dismiss. Only in the modern era did these clues assemble into one picture. Earth is not isolated. It is part of a moving system of debris, fragments, dust, and larger bodies, and that system has shaped the planet repeatedly. Knowing this does not make the sky frightening in a simple way. It makes it more connected. The same population that threatens impacts also delivered samples. The same impacts that destroyed species opened ecological space for others. The same small bodies that preserve dangerous possibilities preserve the chemistry of beginnings. Asteroids make the solar system less static and more historical. They remind us that planetary surfaces are not final forms, but records of encounters. That is the central idea worth carrying through the whole episode. Asteroids are small, but they are not minor. They are fragments of processes too large to witness directly: accretion, differentiation, migration, collision, delivery, destruction, preservation. They connect meteorites in a laboratory to the orbit of Jupiter, a crater in Mexico to the age of mammals, a sample capsule in Utah to the chemistry before life, and a future telescope survey to the safety of cities not yet built. A finished planet hides many of these connections under scale. An asteroid exposes them. Its gravity is weak enough that the surface keeps the memory of small events. Its body is small enough for a spacecraft to map completely. Its material is old enough to preserve the chemistry of the nebula. Its orbit is sensitive enough to reveal the long reach of radiation and resonance. In that sense, the asteroid is not less interesting than the planet. It is more readable. The best asteroid science is therefore patient. It does not ask a small body to be spectacular in the way a ringed planet or bright comet is spectacular. It asks what the object kept: a grain, a crater, a salt deposit, a spin state, a moon, a sample. The answer is often quiet, but quiet evidence can carry 4.5 billion years. That is why the subject can stay calm without becoming empty. The drama is in the evidence itself. Old material, weak gravity, slow forces, sudden impacts, and the long survival of fragments that should have been lost, but were not, ever. Outside on any clear night, the solar system's asteroid population is contributing to what you see, though in an indirect and easily missed way. The Gegenschein, a faint, diffuse glow visible in very dark skies directly opposite the sun, is sunlight scattered by interplanetary dust, much of it produced by collisions in the asteroid belt and by the disintegration of comets. The zodiacal light, a faint cone of light visible before dawn or after dusk extending from the horizon along the plane of the solar system, is the same dust, more concentrated along the ecliptic and closer to the sun. These faint glows are the visible signature of the grinding that has been going on in the asteroid belt for 4.5 billion years. And in the occasional brilliant fireball, a meteor bright enough to cast shadows, sometimes leaving a persistent train of glowing ionized gas, occasionally followed days later by the news of a recovered meteorite somewhere in a field, you are watching a piece of the asteroid belt arrive at Earth, making its final, luminous journey through the atmosphere after 4.5 billion years of patient orbiting. Most of the meteorites that fall to Earth are fragments of S-type and C-type asteroids, delivered by the same Yarkovsky resonance mechanism described earlier, taking roughly 10 to 100 million years to migrate from the main belt to an Earth-crossing orbit and then arrive as fireballs. The freshest information in those meteorites, the cosmic ray exposure ages measured from the accumulation of nuclear reaction products while the meteorite was a small, exposed fragment in interplanetary space, is typically 10 to 100 million years. Before that cosmic ray clock started ticking, the material in the meteorite had been sitting deep inside an asteroid since the solar system formed. Pick up a meteorite and you are holding a piece of the solar system's formation. 4.5 billion years old, arrived from somewhere in the main belt, carrying in its mineralogy and isotope ratios a record of conditions in the early solar nebula, the thermal history of its parent body, the collision that freed it, and the 10 to 100 million years it spent as a small exposed object before the Earth's gravity caught it. The universe sends us free samples constantly. We just have to know what we're holding. Meteorites are the part of asteroid science that can be held in the hand, and their classification tells a parallel story to asteroid taxonomy. Chondrites are the primitive meteorites. They are called chondrites because they contain chondrules, and they are prized because their bulk chemistry often resembles the composition of the Sun, minus the volatile gases. This makes them a record of the raw ingredients from which rocky bodies formed. Carbonaceous chondrites are especially important because they contain hydrated minerals, organic compounds, and in some cases amino acids and nucleobases. Ordinary chondrites are the most common meteorites falling on Earth and are linked broadly to S-type asteroid material. Instatite chondrites are highly reduced meteorites whose chemistry has been invoked in debates about the material that contributed to Earth's building blocks. Achondrites are meteorites from bodies that melted. They no longer contain chondrules because their parent bodies underwent igneous processing. Basaltic achondrites, like the eucrites from Vesta, are volcanic rocks from small worlds. Diogenites come from deeper crustal or mantle material. Howardites are mixtures produced by impact gardening, regolith breccias that combine fragments of different Vestan rocks. These meteorites show that some asteroids were not primitive lumps, but geologically active bodies with internal heat, volcanism, and layered structure. Iron meteorites come from metallic cores. Their crystalline patterns, revealed when cut and etched, show slow cooling over millions of years inside parent bodies large enough to insulate molten metal. Stony iron meteorites, including pallasites, contain both metal and silicate minerals, perhaps representing material from core mantle boundaries or impact mixtures from differentiated bodies. They are beautiful, but scientifically their beauty is secondary to what they reveal. Small bodies in the early solar system became hot enough to separate into metal and rock, just as planets did. This is why a meteorite collection is not just a cabinet of strange stones. It is a set of samples from vanished worlds. Some meteorites come from surfaces, some from crusts, some from interiors, some from cores, some from primitive parent bodies that never melted. Together, they provide laboratory access to parts of the asteroid population no spacecraft has yet visited. Some asteroids are valuable not because they are typical, but because they are strange. Phaeton, the parent body of the Geminid meteor shower, behaves partly like an asteroid and partly like a comet, shedding material near its close approaches to the Sun despite lacking the classical icy activity of a normal comet. Active asteroids in the main belt produce tails or dust clouds while occupying asteroid-like orbits. Some shed material after impacts. Some shed material because they spin too fast. Some may expose buried ice. Others fracture thermally as they heat and cool. Each mechanism produces a different kind of activity, and distinguishing them is part of the modern small body science. This matters because the old categories were created before we had enough examples. The solar system does not always respect human classification. There are icy asteroids, rocky comets, extinct comets masquerading as asteroids, active asteroids with no obvious ice, and interstellar objects whose nature is inferred from a brief, incomplete passage through the inner solar system. Small bodies are transitional by nature. They carry memory from different regions and then migrate, collide, and change. One of the most interesting things about asteroid surfaces is that gravity is almost absent but not entirely absent. On a small asteroid, a person could in principle jump faster than the escape speed, though in practice no one would stand there without anchoring. Dust grains can be launched by tiny impacts, electrostatic effects, thermal cracking, or spacecraft contact. Boulders can migrate after seismic shaking. Regolith does not behave like sand on Earth, because weight is so weak that cohesion, van der Waals forces, and electrostatic charging can compete with gravity in ways unfamiliar from terrestrial geology. A slope can remain steep not because the material is strong in the usual way, but because the forces holding grains together matter more when gravity is tiny. This is why landing on an asteroid is not simply landing on a small planet. There may be no reliable down in the intuitive sense. A spacecraft must navigate around irregular gravity, uncertain surface strength, loose material, and escape speeds measured in centimeters or meters per second. Touching the surface can change the surface. Sampling can disturb the body. Even defining an orbit around a tiny irregular object is difficult because solar radiation pressure and the asteroid's uneven gravity field both matter. Asteroids are small, but operating around them is not simple. And that is why asteroids deserve a full story of their own. They are not simply leftover rocks. They are unfinished planets, shattered cores, water-bearing archives, carbon-rich chemical stores, rubble piles, impactors, meteorite sources, Trojan fossils, and future spacecraft targets. They preserve the first solids of the solar system and still move through the present with enough consequence that we watch them carefully. A planet shows what growth can become. An asteroid shows what growth was made from. And we leave them there, small worlds with long memories, quiet enough to seem insignificant, and old enough to carry the beginning of everything familiar. Good night.